Welcome back, students. Today we are going to continue our discussion of Schrödinger's wave equation, and we're going to talk a little bit about the general strategies to solve it. Solving the wave equation will require a specific problem, and we will encounter many of those as we continue on in this class. But today we're going to develop some keywords and terms that will help us understand exactly what's going on here as we attempt to solve these problems. And as you can see by today's title, one of those keywords is going to be eigenfunctions. So if we take another look at the wave equation, we can see that, again, it is a differential equation. So we have our function that we need to take two derivatives of. We're adding it multiplied by some potential function, and we're returning that same function multiplied by a constant. And you've probably never seen equations like this before, unless you've taken some advanced math. And it may or may not be at all obvious how to go about solving this. So that's what we're going to look at today. So the learning goals for today are going to be the definition of these terms, so eigenfunctions, eigenvalues, operators, and observables, and how we use those. And then what we want to do is be clear to distinguish between wave functions and eigenfunctions. So we're going to get a lot of terminology here, and those two are very important terms, and they're also sometimes the same thing, sometimes not the same thing. So we want to be sure we can know what we're talking about when we use these terms. So to start, we want to figure out what all these terms are and what we're actually trying to do with quantum mechanics. So remember, last time we discussed that the wave equation, the wave function, doesn't actually have any physical meaning. And how do we get meaning out of the wave function? Well, we have to do some sort of operation on it. So when I say operators, what do I mean? Mathematically, when I talk about operators, I mean things that you do to functions. So one example of an operator is shown here, taking a single derivative of a function. And physically, an operator is going to correspond to doing some sort of physical experiment on a quantum mechanical particle. This can be something like trying to figure out what orbital the electron's in, if you're talking about an electron around an atom. And it has a corresponding observable, and we'll look at some of those as we go. And so an operator is something you do to a function, some measurement you perform, some math that you do, and an observable corresponds to that operator, and it is the value that you get after you operate on a function. So if we were to use a position operator, and we'll look at these in class next time. If we look at position operators, if we were to measure a quantum mechanical particle with a position operator, we would get the position out, or we could get the momentum, or we could get the energy. Now, by looking at an operator like this, and so again, derivatives can be examples of operators, integrals can be, multiplying by constants, basically any sort of mathematical thing you can do can be considered an operator. And your intuition should tell you that in general, if you were to do an operation on a function, you're going to return a different function. And we'll look at some examples of this. But if you took the derivative of x squared, you're going to get 2x, right? You're going to get a fundamentally different kind of function. It's no longer x squared. It's on a parabola. Now it's 2x. It's a line. But there are some functions in which when you operate on them, you return the same function. And these are a very specific kind of function called an eigenfunction. So let's go and do some math and look at some specific examples of functions and operators. All right, so here we have the same operator that we did in the slide, a simple derivative. Now let's look at some functions. So if we were to take a function that was equal to 3x squared plus x, and we were to apply it to this operator, we could write operator operating on our function f of x, and this is of course equal to the single derivative of 3x squared plus x. We can do that. That's going to be equal to 6x plus 1. Now we can see that this function, after we've operated on it, is not the same type of function that we had before. So we can't actually rewrite this function based on f of x. We have not just got our function back out. And that makes sense. That's kind of how derivatives work, right? But there are, of course, a variety of functions for which this is not true. So, for example, what if we had a different function? Let's call it g of x. And our g of x is going to be e to the 3x. Well, now if we were to operate on our function g of x, we would take the derivative with respect to x of e to the 3x. And what we get from this is 3 e to the 3x. And another way we could write this is, of course, 3 times g of x. So with this function, with e to the 3x, when we operated on it with our operator that's a single derivative, we actually return our input function, e to the 3x, multiplied by a constant. So e to the 3x is an eigenfunction of our operator was single derivative. And this 3 that comes out is the corresponding eigenvalue. So hopefully at this point, you're recognizing that e to the 3x is not the only eigenfunction to this operator. In fact, if we took another function, let's call it h of x, and we said it was e to the 7x, right? Now, if we were to operate on h of x, what we would return is 7h of x, right? H of x, which is e to the 7x, is a different eigenfunction, and it has a different eigenvalue. And this is going to be, in general, true for all of our functions. For example, we saw this before. I'll go ahead and write this out now. But our Schrödinger equation can be rewritten in the following form. We can write it as h psi of x equals e psi of x, where h is our operator and e that we get out as our energy. And so in this case, our h operator is a little bit more complicated than one derivative. It's negative h bar squared over 2m times 2 derivatives with respect to x plus the potential energy. And so you can see if we were to take this operator out here and apply it to our wave function psi of x, we would get the Schrödinger equation. Now, this equation, it's denoted h there. And that h is for Hamiltonian, and that is due to historical reasons. But the Hamiltonian is the total energy operator. And what that means is when we operate on a wave function with our Hamiltonian, with our total energy operator, what we get are two things. We get wave functions, the solutions that solve this operator, and those are going to be the wave functions for our particular problem of interest. And we also get eigenvalues that correspond to the total energy. So for example, if we were to take our Hamiltonian and adapt it to a three-dimensional system, and then use a Coulombic potential energy, and this would correspond to the location of an electron around a nucleus, we would solve that. The energy values we would get would tell us the energy values of that single electron orbiting the nucleus, and the functions we would get would tell us the wave function of that electron. And if we do that, and we will do this in about a month, what we'll see is that we get the energy values that are exactly the energy values of the hydrogen atom, assuming we have a nucleus with one proton. And the functions that we get give us the probability density of things like the 1s orbital, 2s orbital, 3s orbital, 2p orbital, and so on. So our wave function, so you can see here how our Schrödinger equation is going to be essential for quantum mechanics. So it's going to give us our energy values that we can measure, and then it also gives us the wave functions that kind of determine the properties of these particles. So now what we want to do is we want to talk about how we can work with these eigenfunctions and these eigenvalues and what we can actually do with them now that we know that they exist. And eigenfunctions have a couple of unique properties that help us work with them and greatly simplify a lot of the quantum mechanics that we have to do. The first one is that eigenfunctions are orthogonal. Now, hopefully you guys remember from some math classes that you've taken that orthogonal is a fancy word that we use for perpendicular. And so if we're thinking about vectors, which we were when we first learned about this word orthogonal, we can have perpendicular vectors that mean they have no overlap. So for example, the x and y axis are perpendicular. There's no, the y axis has no x component, the x axis has no y component, and the same with the z axis. And what orthogonal meant when we were talking about vectors is that if we took the dot product of those two vectors, that equaled 0. And so you can imagine, and you've done this before in math, you can imagine other vectors that aren't the straight x and y axis that still, when you take the dot product of them, they get 0 because they have this 90-degree angle. But it's not obvious what a orthogonal function is. It has a similar mathematical definition. So instead of the dot product being 0, an orthogonal function satisfies the following condition. So you can have a set of orthogonal functions if, when you take the complex conjugate of one of those functions and multiply that by a different function in the same orthogonal set, and you integrate that over the variable of interest from negative infinity to positive infinity, you get 0. So this tells us that our eigenfunctions have no direct overlap, you can say, with each other. And this is a property that you want to memorize, and we're going to use this often throughout derivations to greatly simplify things. And you'll see how that's done as we go forward in this class. Remember, one of the things we want to do with our wave functions is we want them to be able to mean the probability of observing some sort of observable. And for that, we have to be able to set our wave functions to mean something in terms of probability. And like we talked about last time, probability is a number between 0 and 1. So the way we do that to wave functions is we normalize them. And I mentioned this last time. I'll go through it in a little bit of detail here. But the normalization of a wave function is a property that's going to be kind of similar to the orthogonality of wave functions. So for a wave function to make physical sense, we need to have the following. When we integrate that wave function, and here the distinction is instead of having the j subscript, here we have an I subscript. So if we have our set of wave functions, if we were to take one of them, or our set of eigenfunctions, and we were to take one of them, multiply it by any other function, integrate that, we get 0. However, if we take one of our eigenfunction solutions to a particular problem, multiply it by itself, and integrate that, we need to get 1. And this is a process that's pretty easy to ensure we get 1. Essentially, what we do is we just slap a normalization constant on there. So if we were to integrate some function and instead of getting 1, we got 10, all we do is then divide that function by the square root of 10. So then we multiply it by itself. When we square it, we end up by getting 1. And we'll go through some examples of this in class. So if we have functions that are in a set of functions that are orthogonal, and they're also normalized, what we have is actually an orthonormal set. And so these two terms, the normalized and the orthogonal definitions here of our eigenfunctions are going to come into play often over the course of quantum mechanics. So keep these in the back of your mind. The last thing we want to note here about our eigenfunctions is that not only are they an orthonormal set, they're also what's called a complete set. So what do I mean when we say the functions have a complete set? So let's think about this example. So again, here's our Hamiltonian operator. This is our Schrödinger's wave equation. And let's say we want to figure out the energy of a certain quantum mechanical system. So we operate on that system, and that's going to depend on what our wave function is. So let's ask the question of what if my wave function is actually an eigenfunction of that operator? And the way we're going to denote eigenfunctions is commonly like this. So here we can see we have a psi sub n, where that n can be any integer, sometimes including 0, sometimes not. We can have psi1, psi2, psi3, and so forth. And that's going to have an eigenvalue of e1, e2, e3. So if your wave function actually is an eigenfunction of the total energy operator, the Hamiltonian, what's going to happen if we operate on it? So if we operate on our psi2 here, we're going to get our psi2 multiplied by e2 every single time. And that's what it means to be an eigenfunction. So if my wave function psi of x is an eigenfunction of the total energy operator, if I seek to measure the total energy, I will always return the same value. In this case, it's going to be E2, whatever energy corresponds to that. But what if my wave function is not an eigenfunction of the total energy operator? What if it's something else? So we saw on the iPad example that that's certainly possible. We had an operator that was taking a single derivative, and we had a function that was 3x squared plus x. And that does not fit our nice eigenfunction eigenvalue relationship. So then what happens if I seek to measure the total energy? Now, what happens is we actually get one of the eigenvalues, and that's because eigenfunctions form a complete set. And so what that means is that we can take any function, in this case, or it's our generic function psi of x, and we can add together all of our eigenfunctions, and we can return any function that we want by adding different components of our eigenfunction. So let's go through an example of how we would do that. To show you how eigenfunctions form a complete set, I want to go through a Fourier series. So what I have here is an example of a function that almost looks like a wave, right? But it's clearly not a sine wave. So what we have is essentially we have a jigsaw pattern where it goes up and down with these sharp points. So if I compare this, and this is actually to a cosine curve, but you know they're related. If I compare this to a cosine curve, we can see that the cosine curve does a pretty poor job of recapitulating this this sawtooth pattern, right? We have curves, we don't have points, and we're pretty low instead of being high. Now, what we can do to actually approximate this is start adding in more terms. So here, this function that I'm showing in green is this y1, and we have a single cosine term here. In each of these successive functions, y2, 3, 4, and 5, I'm going to add more cosine terms. So if we go from y1 to y2, we can see that it gets a little bit sharper and a little bit closer to this ideal sawtooth pattern. And you can see it's kind of doing some weird sine stuff here. It's curving, of course, because it's made of some psi functions. But it's getting closer. Now, what if we add more? Let's go in and add one more function for y3. Again, we can see it's getting closer. And if we go one more again, we can see for y4, it's getting even closer. So now we almost have this point here. It doesn't quite look as perfect because it's not as perfect, but it's getting kind of close. Now for this last one, I've added in not one term, but 4 more terms here just to kind of show when we get a good fit. And here we have our final function. Let me click out of this. So here we can see that this function that's made exclusively out of cosine functions is starting to look pretty good compared to our function that only has straight lines. So again, going back to our original function, we just have straight lines. Now, if we get rid of those and bring up our function that's made out of exclusively cosine functions, we can see that we're getting pretty close to a series of straight lines. And this only gets better the more terms we add in. So these cosine functions form a complete set, and in theory, we can bring out any function by combining certain amounts of sine and cosine functions in certain ways. And so the wave functions are the same way. If our wave function looked like this, it was a sawtooth pattern instead of a nice sine curve, we could put in a certain number of sine curves, or in this case, cosine terms, and recapitulate that function exactly. Now, what that means for us in terms of what we're going to measure is we could measure any single one of those terms that is a part of our wave function. So if we go back to our PowerPoint here, if our wave function, capital psi of x, is equal to b1 small and psi 1, where the psi 1, 2, and 3 here are the eigenfunctions, we would measure each of the possible energy values that are associated with psi 1, psi 2, and psi 3. Now, what we would measure depends on how much the function looks like psi 1, psi 2, or psi 3. And that's what these B constants here are. And we'll look more at these in the coming lectures. So don't worry too much about how we're going to do that yet. We'll see that in the next couple of lectures. But just know that we can operate on any function. It does not have to be an eigenfunction. So this is the distinction I was mentioning at the beginning of class, where we have eigenfunctions that are specifically solutions to some operator, but the actual wave function is made up of a variety of these eigenfunctions. In fact, what we would say is that it's a quantum superposition of all of these eigenfunctions. So before we make a measurement, it could be any of them, and then once we make a measurement, we're going to force it into one of those functions, and we'll see some examples of that as we go forward. So the next thing we're going to look at in the next lecture is how to apply these ideas that we've talked about using eigenfunctions and observables, eigenvalues, operators, how we apply those to quantum mechanics in general. So we're going to look at what's called the quantum mechanical postulates that tell us how to use these equations. And then once we look through those, we're going to look into applying these for the first time to our first quantum mechanical system, the particle in a box. Before I let you go, I want to just conclude for the past couple lectures some of the key points that we talked about. So we decided that quantum mechanics is appropriate to use if we have sufficiently quantized energy. So if the energy gaps between the steps are large compared to the thermal energy available, and if the wave nature of a particle is apparent based on the scale of the experiment. We talked about traveling waves, and we especially focused on standing waves that are of special interest to us because they represent states where the observables don't change with time, which is what we want to do when we're measuring things. We don't want to deal with changing energy as a function of time. We looked at the Schrödinger equation and saw how this describes the energy of our wave particles, our quantum mechanical wave particles. And then we talked about a little bit of how to solve the Schrödinger equation. So the Schrödinger equation is a differential equation that has eigenfunction solutions that return eigenvalues, both of which are useful for us. In this class, we're not going to do too much in terms of actually solving these equations. We will for the particle in the box that we'll go through first because that's pretty simple. But for then every other more complicated system, we're going to rely on the mathematicians of the past and just be supplied with the answers. And we can easily check if there's solutions, and we'll do that as it comes up. And the last point to talk about is that a wave function can be represented as the sum of the eigenfunction solutions to the total energy operator, the Hamiltonian, or any operator. And we'll look at the interplay between operating on eigenfunctions with different, or wave functions, sorry, with different operators. And we'll start talking about that next lecture, and then we'll go into that in more detail when we talk about things like the uncertainty principle in the future. So with that, I'll let you go. This lecture was a little much shorter compared to the last one, and I look forward to seeing you guys on Wednesday.